So, do you remember in January when we didn't have this coronavirus and we did this question? Um, we This was our basis of derivatives. We found the average value of this car. We were trying to figure out how fast it was going at A. So we could get the average values, but then we learned later on that we could actually find the speed at one point, say B, by finding the derivative. And remember, derivative was a slope, so derivative would have been y, which is the distance, over x, which is the time. So derivative was a slope. Then I asked you to calculate the surface area of this pond, and you did in different ways, you used different shapes. Now in calculus, I'm going to make all rectangles, and I'm going to make all these rectangles a specific length of delta x, and all of them have a certain height. They're different, so f of c is like the y value. Since they're different, we're going to call it f of c sub I, because c could be different. And the areas are the base times the height. So like if you remember or just recall what we just did, the derivatives or the height divided by the base. We're talking about integrals now, and we learned that integrals are the opposite or inverse of derivatives. So integrals would be bases not divided by, or not height divided by bases, but bases times height. That would give you an area. I hope that kind of makes sense. So for derivatives, we're doing y divided by x. For integrals, we're going to be doing x times y. In terms of shapes, x times y. So that is a very basic explanation of what a definite integral is. If we took all those rectangles here and added them all together, it would be the sum, that's what this big sigma means, of the heights, each height times each width. So you're adding up a certain number, n is the number of rectangles. So in this case, we had maybe, if you count them, maybe, let's say 32 rectangles. So that would be 32 rectangles. So we're adding the first through the 32nd rectangle, the areas of the first through the 32nd rectangle. This is called a Riemann sum. Now, if we had more time, if we were in class, we'd spend a lot of time explaining what that is. But lucky for you, we're going to cut to the chase. If you take, that's going to approximate the area, which you already did. But if you took an infinite number of rectangles, so all those, if you had an infinite number of rectangles, you would have their actual widths would go to 0, and they would exactly get the area of this pond. So this is the whole idea behind a definite integral. Definite integral will take the sum of this certain number of rectangles, but not certain number. If we take the limit as n goes to infinity, now we have an infinite number of rectangles, and this will be an area. Now, how that relates to integration is this. We're going to call this a definite integral. So this is really where we're focusing on in this section, definite integrals. And for no reason right now, we're just going to call this area a definite integral. You'll see how it relates to your integrals in the next section. But A definite integral has limits. So I have a little number here, a, that's called the lower limit, a number up here, b, that's called the upper limit. So what that means is you're just integrating from lower limit, you can think of left, from some left value to upper limit, you can think of some y value, and that equals this area calculation that we were just talking about. So I know that's probably confusing. I wish you could ask questions as we're going on. Definitely do email me with questions or whatever, but this is the big theorem of this section 4.3. The area of a region is the definite integral of the function between a and b. One thing that needs to be pointed out is if you're going to find, this is basically the area under the graph. If you're going to call it area, f must be continuous and non-negative. In other words, your function has to be above the x-axis. If it's not, it's going to calculate a negative area, and we'll see that. So I'm going to stop right here because this is getting longer than I wanted to in the first place. And we'll start with an example of this with the next video that should clarify things, hopefully.